नमस्कार, हम हैं आदित्य और सौम्या।
और आपका स्वागत है घटना चक्र के इस नए और ज्ञानवर्धक सफर में।
Welcome back to the deep dive. Okay, so we all think we know solids, liquids, gases, right? Pretty straightforward stuff. But here's a question that might actually make you stop and think for a second. What element is found in liquid form at normal temperature and pressure? Now, most people, I bet, instantly picture mercury. You know, that silvery metal.
The classic example.
Exactly. But what if I told you there's another answer? And this one's a nonmetal.
Yeah, it's funny how our everyday intuition about how elements should behave can sometimes miss the mark, isn't it? These fundamental properties, they often hide some really surprising detail.
They really do. And today, we're diving deep into the world of halogens. Specifically, we want to shine a spotlight on that pretty unique liquid nonmetal, bromine.
That's the mission.
Yeah, we want to unpack why it stands out. Maybe compare it a bit to its family members, fluorine, chlorine, iodine. They're pretty interesting too.
Oh, absolutely. A fascinating group.
And then pivot to how these sort of quirky properties are actually being used in some really cutting-edge energy research. We're drawing on some great sources today. There are excerpts from a piece called Energy Hatale, and also a really cool study from Nature Energy.
So get ready for, I think, some genuinely surprising facts. Hopefully you'll get a clearer picture of some fundamental chemistry that, really shapes our world.
Maybe a few moments along the way.
That's the goal, understanding why elements do what they do.
Okay, let's tackle that opening question head on then. The element, the non-metal element, found in liquid form at normal temperature and pressure, besides mercury.
It is indeed bromine, Br2.
Right.
That's the one. And bromine is, well, it's really in a class of its own here. It's the only nonmetal that stays liquid at what we usually call room temperature and pressure.
So like 25 degrees Celsius, 1 atmosphere.
Exactly, around that mark. Its melting point is actually pretty chilly, minus 7.2 degrees C, but it doesn't boil until 58 degrees C. So you see, that gives it quite a wide liquid range under conditions we'd consider normal.
That's a fair range. So if we zoom out a bit and think about all the elements, not just nonmetals, we're saying there are actually two elements commonly found as liquids under these normal conditions.
That's right. You've got mercury, the metal everyone thinks of, and then you have bromine, our non-metal outlier.
But it's quite striking, isn't it, that these two just sort of defy the usual solid or gas state at everyday temperatures.
It is, and it's not just a weird quirk. It really speaks volumes about the incredibly diverse properties elements can have. These two are definitely outliers in their categories.
Right.
And understanding why they're liquid, well, that opens up a lot of insight into chemistry.
That makes me think about bromine's family then. Because the halogens, group 17 on the periodic table,
Yes.
they actually show this amazing range of physical states, don't they? Even though they're chemically quite similar.
Oh, it's a perfect example. A really clear progression as you go down the group. So right at the top, you have fluorine, F2.
Okay.
That's a gas, a light green-yellow gas, and it's extremely reactive. And the key thing about fluorine really is that it's the most electronegative element there is.
The strongest pull on electrons.
Exactly. It wants electrons more than anything else, which is why it's so incredibly reactive.
Okay, so fluorine's a gas.
Yeah.
Then next down.
Next is chlorine, Cl2, also a gas at room temperature, often described as, a lighter gas.
So it's a killer gas.
Right. Then we come to bromine, our liquid.
Our liquid anomaly.
Precisely. And then we get to iodine, I2. Now, iodine is different again. It's a solid under normal conditions.
A solid, okay.
And this is where it gets really quite cool. Iodine shows this phenomenon called sublimation.
Sublimation.
Oh.
I remember that. That's where it skips the liquid state. Goes straight from solid to gas.
You got it. Skips it completely. When you heat solid iodine, it doesn't melt into a liquid first. It turns directly into this beautiful purple gas. And, the reason for this amazing progression, gas, liquid, solid, as you go down the halogen group, it actually comes down to something called London dispersion forces.
Intermolecular force.
Exactly. As the atoms get bigger going down the group, they have more electrons. These electrons can slosh around, creating temporary, uneven distributions of charged temporary dipoles.
Yeah.
These temporary dipoles induce dipoles in neighboring molecules, leading to weak attractions. The bigger the atom, the more electrons, the stronger these London dispersion forces become.
So for fluorine and chlorine, they're too weak to hold them together as liquids at room temp.
Right. For bromine, they're just strong enough to keep it liquid, and for iodine, they're stronger still, locking it into a solid lattice.
But still weak enough that heating it makes it jump straight to gas, the sublimation.
Precisely. It overcomes those forces directly into the gas phase.
That whole idea of needing a certain amount of energy to make these changes happen, melting, boiling, sublimating, that brings us neatly to the concept of transition temperature, doesn't it?
Absolutely, that's the term we use. A transition temperature is just the specific temperature where an element or compound changes its physical state.
So like bromine's melting point, minus 7.2 C. That's a transition temperature.
That's one, yes. And its boiling point, 58 C, is another.
And for iodine, it's sublimation point.
That's also a transition temperature. It marks that specific point where the solid transitions directly to gas under standard pressure. It's a fundamental property, reflecting the energy needed to, overcome or form those intermolecular forces we talked about.
It's really quite elegant when you lay it out like that, these fundamental properties, these everyday states of matter, leading to these unique behaviors. But for me, the really exciting part is when this stuff jumps out of the textbook, and into actual real-world applications, like that study you mentioned in Nature Energy.
Yes, exactly. That Nature Energy study is a fantastic example. So what this research group did was construct something called a multi-electron transfer cathode, and they based it on bromine and iodine.
Okay, multi-electron transfer. What does that mean in practice?
Right. So the really clever bit here relies on the fact that bromine and iodine can exist in multiple oxidation states. Basically, they can gain or lose different numbers of electrons quite readily.
Ah, okay.
This ability allows them to handle multi-electron transfer in electrochemical reaction. They can shuttle more than one electron per molecule during the charge-discharge cycle in a battery.
Which means more energy storage.
Potentially, yes. More electrons transferred generally means you can store more energy for a given amount of material, so it could lead to batteries with significantly higher energy density compared to some traditional materials. It's a direct application of their unique chemical properties and reactivity we've been discussing.
Wow. Taking that liquid nonmetal and that sublimating solid and putting them to work like that.
It's pretty neat.
So wrapping this up a bit for you listening, what have we really uncovered here? We've seen how bromine is, well, pretty special. It's the only liquid nonmetal at standard conditions.
Standing out from its family?
Yeah, and how it fits into that slightly bigger picture. With mercury, the two common liquids, we explored that whole halogen family, that amazing range of states.
From the gases, fluorine and chlorine,
To liquid bromine,
and solid iodine, the sublimator.
all linked back to those London dispersion forces, getting stronger down the group. We touched on transition temperature, just the point where states change. And then we saw how bromine and iodine aren't just textbook examples, they're actually part of cutting-edge energy research.
Right, potentially boosting battery performance through that multi-electron transfer idea.
It really is fascinating, isn't it, how these fundamental properties, things that seem quite simple, like whether something's a liquid or a solid on your desk, can lead to such unique behaviors.
Absolutely.
And how they can pave the way for completely new technologies. It really makes you wonder, doesn't it? What other seemingly simple properties of elements, maybe things we take for granted, might be hiding these kinds of groundbreaking applications?
Or even what other everyday substances might hold surprising secrets about their own state transitions, secrets we're maybe only just starting to figure out. Lots to think about.